there and welcome to this Wi-Fi sheep tutorial with me, Tom. Now, with Christmas coming up, I'm sure many of you have or are going to receive a Raspberry Pi, or maybe you've had a Raspberry Pi board for a few years now. Something like, I don't know, A+, Pi 2, something like that. And they've sat around and you've sort of played with it a little bit and not done anything else with it. Have you actually wanted to simply program a computer for the first time and have been really frustrated of not being able to get to grips with the languages or even how to start? Well, do not fear. In this tutorial video, I'm going to show you how to program a Raspberry Pi computer, from setup through to actually getting the machine running to putting our first code in. Now, we're going to start from the beginning, but we need to assume that you're comfortable using a computer, either a PC or Mac, have one available in order to write some data to, and you also need to have a Raspberry Pi board. If you can follow what we do, then you stand a good chance of being able to program your first computer. For this tutorial, you'll need a Raspberry Pi single board computer. It doesn't matter which type you use, but be aware the smaller Pi Zero models will require additional adapters for USB and video link-up. You will also need a USB keyboard and a video lead. We're using a 1/4 inch to RCA phono composite cable, but most Pis also support normal HDMI video leads. You will need a mains power transformer with a micro USB plug. We're using an official Raspberry Pi power supply, but whatever you use, it must output 5 volts at least 2 amps. Check before plugging in. To store data, we need a micro SD card. This doesn't have to be a new or large card, just 2 GB is sufficient. However, any existing data on any used card will be lost. If your PC or Mac does not have a micro SD card reader, then you will need an SD or USB adapter. These can be sourced very cheaply online. Next, we need to visit the official raspberrypi.org website and click the red Downloads tab. On the Downloads page, scroll down to the bottom and click on the Ichigojam BASIC icon. This will link you to the official site. Scroll down and click on the Downloads button. Now scroll down and click on the red Downloads button to start downloading the required files. Next, and using an adapter if needs be, plug your micro SD card into your computer. On Windows, by right-clicking the drive, or on Mac by using the Disk Utilities tool, wipe and reformat the SD card, making sure to use the MS-DOS FAT or FAT32 file formats. Now find the downloaded zip file and open or extract the contents. Next, copy all the extracted files to the freshly formatted micro SD card. One additional extra, if you're using the composite phono leads for video output and live in a PAL country, you might want to change the video output mode. To do this, open the config.txt file in Notepad or TextEdit and add the line sttv_mode equals 2 before saving the file. Moving on, we can now set up our Pi board. For this tutorial, we'll be using a Raspberry Pi A+ model. First, take the micro SD card and place it into the underside slot on the Pi. If your Pi does not have a case, then place the board on top of the anti-static bag it came packaged in. Next, we'll plug the 1/4 inch 3-way phono cable in. If you're using HDMI instead, then plug that cable into the adjacent socket. Now plug the power transformer in, making sure it's still unplugged at the mains end. Finally, add your USB keyboard. If you're using a larger Pi board, such as the Pi 2 or 3, then it will not matter which USB socket you plug into. Now plug your video lead into your TV. In this case, the phono lead was not wired the normal way. So instead of coming from the normal yellow composite jack, the video was found to be outputting from the red jack. In this case, just plug the red jack into the yellow socket. Before powering up your Pi, switch on the TV or monitor and set it to the correct AV mode if using composite, or HDMI if using a HDMI cable instead. Finally, plug in the power transformer into the mains. If all has been set up correctly, the Pi will light up as it boots. So there we go, we're just waiting for the Pi to boot up. And there we go, it actually boots in under 2 seconds on the Raspberry Pi. Even the slower and older Pi boards, such as the Pi 1 originals, and things like Pi 0, A and B+. Anyway, there we go. So this is the boot screen, which we're welcomed with. This is standard for Ichigojam BASIC. We're running version 1.2.0 for the Raspberry Pi here. And you can see it's the last line of text says OK. So it's now simply loaded BASIC and waiting for an instruction. Now, BASIC is the programming language which this distro uses, and BASIC actually stands for Beginner's All-Purpose Symbolic Instruction Set Code. Now, you don't really have to remember that, but it's an interesting footnote. BASIC's been around for a very long time, from about 1969 onwards, and it was sort of on the very early 70s computers right through to the 80s micros. So your Sinclair Spectrum, your Apple II, your BBC Micro, Commodore 64 would have all had a version of BASIC. Now, you might be thinking, is BASIC relevant in the sort of modern age? Well, I think it is. It is, as it says, a basic language, but if for a very first programming language, it is ideal for learners as it was in the 1980s. So, let's get going. Okay, so we'll start by, let's just type something into the computer. Now, of course, with this distribution, we've only got the keyboard to input data into the computer. So it's simply waiting for an instruction. So let's just type Tom, which is my name. So let's just say Tom, see what happens. So I'm going to hit enter or return on the keyboard. And you'll see it actually reads as syntax error. That means that it didn't like what I put in or couldn't understand it. That's fine. Throwing errors in code, it happens all the time. It's completely normal and it's nothing to worry about. So that didn't really do anything, just threw an error, but let's not worry about that. Let's try putting a number in. Let's say 29. So I'm going to hit return or enter again. Now you'll notice that it kind of accepted 29. It didn't do anything, but it didn't throw an error. So we can already tell by that that it likes numbers more than it does letters. I'll explain about why that happens later on. So that's sort of beginning. It's not programming as such, but we can sort of learn about what we can and can't put in the computer. Okay, let's put an instruction in that will work. So let's find out how much memory we've got to play with. To do that, I ask question mark, type the word free, and then holding down the shift key, I have to open and close brackets, which is shift 9 and 0 on your keyboard. So I now ask free and hit return, and that brings back a number, which is 1024. That's how much memory we've currently got to write a program in. Now that's 1024 bytes. That's not megabytes, gigabytes, terabytes, that's bytes. So if we take the 24, so we round down to, let's say, 1,000 bytes, that's 1K. So we have 1K of memory to put a program in, which in today's modern age of terabyte, gigabyte drives, terabyte drives, that sort of thing, it is nothing. It's a fraction of a floppy disk. It's nothing, but it's kind of good because it gives us a constraint to work to, and it means we can't create large, rambling, complicated, bloated programs. We've got to keep everything very simple, very straightforward. So let's actually try putting a program in. So the first thing I'll do is I'm going to type an instruction to clear the screen, which is CLS. If I type the letters CLS and press return, it says OK, it clears the screen. Now let's try getting our name. When we put our name in, I put Tom in, didn't work. Let's try making it work. So if I type print, and then I go shift, quote mark, and it has to be a double quote mark, Tom, shift, quote mark, like so. And now I press return or enter. You'll notice that now the next line underneath, it actually puts the word Tom on the screen, and it says, OK, done. So it accepted that. But you may notice that we put the line in and executed. And that's fine for single line operation. But what if we want to write a program? We need to be able to put the data in without it executing whenever we hit return. To do that, we use line numbers. So let's make this program a little more complicated and actually make a program. So if you follow along, this is the very first program we're going to do. So let's just clear the screen so we don't confuse things. So CLS. So we now sort of got a blank page, if you like, so we can start. So I'm going to start by typing 10 and print. Oops. Another thing to watch is some keyboards like the one I'm using, the quote marks and the @ symbol are reversed. So, for example, on this British keyboard, Shift 2 is on the keyboard should be quotes, but you'll notice it actually comes back as @ symbol, and Shift @ comes back as quotes. So if I mistype that throughout the tutorial, you know why that happens. It just bear that in mind. So we go 10, print, hello world, end quote, and we'll say 20, end. Now, you'll notice that because I started the lines with numbers, the program didn't execute. So when I asked it to print world, it didn't print world because it had a 10. And then I put 20 underneath, which I set to end. So we've now created a very simple 2-line program, which is going to print hello world on the screen and then end. End means stop running. So how do we start running? Well, if I type run and then I press return or enter, there you go, it executed the program. So if I now type CLS again, that will clear the screen. But unlike before, because we put line numbers in each line of the program as we inputted it into the computer, it's still in the computer's memory. Observe. Let's ask it how much free memory it has now. So now you'll notice we've now gone down to just under 1K, 992 bytes of free memory. That means there's something in the computer. If we want to check what is in the computer, well, we know it's our program, but let's just check it is our program. If I now type list and press return or enter, you'll see there it goes. It lists the program. So that is the program in the computer's memory. And it doesn't matter if I clear the screen, it's still in the memory of the computer. So I can simply type run and it will run the program. Okay, so that's our very, very first basic program. But how can we make that a little bit more interesting? How do we modify the program? Let's clear list. Now we've got those numbers. We've got 10, print hello world, 20, end. What if I want to add another instruction? Well, let's add a line 15. That's why we go up in tens, you see. So it means I can add a line in between 10 and 20. So if I now just type 15, go to 10. I'm going to clear the screen again. Now, what happens if I relist? You'll notice it now goes 10, 15, and 20. So if you enter a new line with a corresponding number, the computer will automatically slot that into the program in the desired place. Okay, let's run this program and see what happens. You'll notice that we're now reprinting the word hello world over and over again while scrolling down the screen. And you'll also notice that if you try typing anything on the keyboard, you're more or less locked out the system. This is because the program is looping. The command go to tells the computer to go back to line 10 and re-execute line 10's line of code. So we're just going round and around and around in a never-ending loop. To stop the loop, we need to hit the escape key once, and you'll now see how it tells you how it's breaks or broken the program. So break in 10 or break in line 10, and it actually tells you what line 10. So it tells you where it was in the program when it stopped running. So if I can just CLS again, list again, and you can see there, so 10, print hello world, 15, go to 10, 20, end. In this program, we never get to end because we're constantly hitting go to 10 and going back to line 10, going to 15 and then back to 10. So line 20 is actually no longer necessary, and it's using up memory in the system. So we could spare some memory by simply typing 20, leaving it blank. And now if I list again, you'll notice that line 20 has been removed from the program. The program, however, will continue to operate perfectly fine. Okay, so how about changing or editing a line if we've made a mistake or want to change a piece of text or information or an instruction? Well, let's clear the screen. We'll list our program again, those two lines. So if I want to make a change to line 10, the quickest, simplest way to do it is just to retype your instruction out. So 10 print. Let's modify that to hi all space, and I'm going to put a little colon on the end. Now watch what happens. You'll notice that instead of printing below the current line, it actually prints next to the piece of printed text and carries on until it ends up scrolling. So the scroll is much slower, but it actually fills the whole screen. And that's what a colon next to a print instruction does. It tells it just to carry on next to the piece of text on the same line where there's space available. If we escape and list, you can see that the new line 10 I put in replaced the old line 10 in the program. Okay, let's clear the screen. And now we're going to wipe that program as we're going to look at doing some variables. So we need to start a new program. So if we type new, and then if I type list, there's now nothing in the computer. And not forgetting to put the question mark in, I can type 3, and we're back up to 1024 bytes. So we have a fresh, clean space ready to start again with a new program. Let's clear the screen. Okay, then what we're going to do now is called variables. What is a variable? Well, if you imagine a box, and let's say we call the box A, and we're going to put a number in the box A. So let's say A equals, let's keep simple numbers here for now. So let's say 20. And it'll say OK. So if I now ask it just to print A, it comes back as 20. If I said B equaled 10, and ask it to print B, you'll notice with the print, I'm not putting quote marks, because if I put quote marks in, so if I ask it to print B, it'll just print the letter B. If I tell it to print B without the quote marks, it'll come back as 10, because you can see we told it what B equaled. So it's a bit like algebra. So A is going to equal 20, B will equal 10. So if I now said print A plus B, it will come back as 30. And this is how we can implement basic maths. So the computer knows what A is, and it knows what B is, so it can add them together, and it equals 30. If I wanted to divide the two, so let's say print, so let's say, A, that's 20, will be divided by 10. It comes back as 2. You'll notice that we don't use the actual divide symbol, we just use the slash symbol. And that's important to remember that with all computer programming languages. That's basically the syntax. Same with times. So if I want to times them together, it's print A asterisk B. So A, which is 20 times 200. So that is how we can do basic maths with the system. Okay, so hopefully you've managed to keep up so far and have been able to follow what we've done. And I'm sure you're probably thinking, okay, that's very good, but I'd like to do something a little bit more complicated, maybe like making a simple game. So let's do that now. Now I've restarted my Pi. To do that on this system, it's simply the case of typing reset. You press enter and you see the computer will then actually reboot. There we go. You didn't have to do that. You could have just gone CLS or type new. Let's just check that we've got the full bank of memory available again. There we go, 100, I keep saying 100, 1024 bytes of memory, or 1K in the system. Okay, let's CLS, let's clear the screen. And let's have a go at writing a simple game. Now, I was thinking maybe look at doing a simple helicopter landing game. So you play as a little helicopter on the top of the screen and you have to land on a sort of helipad or H on the sort of bottom, and you can kind of control left, right, up, down. And that's not too difficult to do in BASIC with the tools we've got available. So let's start putting some parameters in. So first of all, let's start with 10 CLS. We need to clear the screen when we start the program, so we've got a fresh, if you like, piece of paper to actually put our graphics on. 20. Now we're going to put an X and a Y coordinate in. So I'm going to say X equals, no, X is always across. So let's try 20. And I'm now going to use a colon. And I'm going to say Y, it's going to be down, equals, I think I'll say 20 as well. Now you can use colons to actually put lines together. So I could have put Y as 30 and gone Y equals, but if I bank it all onto a single line, separated by colons, I can actually save space, line numbers, and of course, all importantly, memory in the computer. So that's a valid way of doing things. So we've got an X and Y coordinate set up. Okay, so I'm going to jump down a few lines now because I know I want to put some further commands later date higher up in the program. So for now, I'm just going to say 50. And I want to plot our player or character, which is going to be the helicopter, on the screen using those coordinates. Now to do that, I need to do an lc command, which is short for location. So I can say lc location. I don't need to leave a space, so I can go X and then Y. Now you'll notice that between the X and the Y, I've left a comma. So I'm asking coordinates, so with location coordinates X, Y. Now I'm going to use another colon, and I'm going to say print. Okay, I won't put a space in this time. And I'm going to actually print a little helicopter character that's already built in to BASIC. To do that, I want to hold down the Alt key or ALT key on your keyboard, usually next to your Windows icon key or your Apple key if you're on a Mac keyboard. Alt, and then I'm going to press J, there we go. And then Shift to close. Okay, so you see I've actually printed a little helicopter icon on the screen. So enter that. Let's just try running, see what that does. There we go. So you can see it's run and it's put that little character on the screen a little bit further down than I wanted. I want it to start at the top. So CLS list, see where we are. So let's change those X and Y coordinates to something a bit more simple. So 20x equals 15. colon y. Let's have a think. Let's try 5. Let's come right down. Oops, y equals 5 rather. Okay, let's try that. Yeah, that'll do. Can always change it later on. That'll do for now. That's brilliant. So we've got our player plotted on the screen. Now, the next thing I'm going to do is add some input so we can actually control the player on the screen using the keyboard. So to do this, we will open a line at, let's try line at 30. That's why I left some space, you see, between line 20 and 50. So 30. And we're going to set up a new variable called k. And k is going to equal a built-in function built into BASIC called inKey. InKey. Open and close brackets. And what inKey is a built-in function that tells BASIC to listen to the keyboard for you, the user, typing or pressing a key. So what we can now do is define keys on the keyboard that we're going to press to control. So a left and right, up and down. You get the sort of idea. So let's do a left and right. We'll use Z and X on the keyboard for this. So we're going to set Z and X when the program is running to move our little helicopter back and forth. So to do that, let's just CLS and relist so we can see everything in the correct order. And now let's, right underneath, let's say 35. And we're going to say if key, or in this case k, equals, now we're going to need what's called an ASCII character here. It's 90. So if it equals 90, then we need to reduce x. So x is going to equal x minus 1. And that means that the value of x will equal the current value of x, which is 15, but minus 1 to 14. And then it will reprint, you see. So we'll enter that. We need to put a goto loop in as well. So let's say 100. And we'll go to 30, which is where we input the key. So let's just put that, list that back so you can see what's going on. So at line 30, k equals inKey, and it awaits the call. If k equals 90, then x will equal x minus 1. At line 50, we relocate and we print the helicopter character. And then at 100, which is the next line from 50, we go back to 30. So let's just run, see what happens. And you can see that does actually work. The helicopter will move when I press Z, but you'll notice it sort of leaves a helicopter behind it. So we need to blank the first helicopter, delete it off the screen, and then replace it with the second. So let's hit escape, CLS and list. Now we might be able to get away with just refreshing the screen. So if we put a line 99 in and say CLS, there we go. You can now see that it's refreshing the screen each time, and so it wipes the old helicopter. Okay. So now I'm going to put in line 36, which is if k equals, now if z goes one way, x needs to go the other. So I'm just going to find x, which is 88. So if k equals 88, then x
equals x plus 1. And there we go. We can now go back and forth like so. Now, I mentioned about how to find the ASCII character. You can actually ask the computer to generate what the key code for the character you want to use is. So for up and down, I want to use what will be the backslash or question mark key. So if I can now simply on the fly type print ASK open bracket speech mark, put our key press within the speech mark, close bracket, and you see it comes back with 47. So I now know that my down key will be 47. So let's go back to my list. List CLS, there we go. So it's 47, so I can say 37 now. If K equals 47, then in this case, Y will equal Y. And we're going down, so we want to say plus 1. Let's just run to check that works. So we can go left and right, no problem. And we can now go down, no problem. Let's CLS, list again. And I'll now put the instruction for going back up. So we'll put that in as a line 38. If K equals, and we need to actually, before we do that, we need to find out what the up key, which I'm going to use the at or quote mark key. So let's find out what that is again by going print ASC open bracket close bracket 39. Okay. So line 38, if K equals 39, then Y will equal Y minus 1. And there we go. We've now got a helicopter that can more or less fly around the screen. Okay, so we've got that working, but now it'd be nice to have a actual helipad to try and land on. So let's just escape the program, CLS and list. So what we're going to do now is we'll add a new set of variables for the location of the helipad. So let's put it in at line 21. Line 21. This is going to be slightly confusing, but we need a new X and Y. So we'll just say, let's just say H will act as our X. So H will equal 15 colon, and let's just for argument's sake say J, which can be our Y, will equal, let's say 20. Okay, let's just check that's fine. It's happy with that. Yes, it is. It won't make any changes at the moment. Okay, so next thing we're going to do is we need to plot the actual helipad onto the screen. Before that, though, you'll notice line 99, CLS, that's why I'm redrawing to allow us not to have sort of multiple helicopters on the screen at one time. We need to move that because I want to fit my helipad underneath it, and we see we've got 99, 100. So I need to move CLS, so I'm just going to say 99 blank, and that will delete that line. And let's just put CLS at line 70. So I now retype 70 CLS. CLS again, we'll clear the screen. Now if I list you should see CLS has moved up, and that gives us a space underneath. So, for example, now at line 75, I can say location, and we don't want XY this time, we want H, comma, J, colon, print, open speech mark, H, close speech mark. So if we run that, you notice unfortunately the helicopter is somewhat flashy, but at least we can now see we've got a H on the screen for our helipad. And there are ways we can fix that flashing, but we'll leave it there for now. Okay, so let's CLS. List again. Now what we need is a way for the computer to know when the helicopter has actually touched the helipad. So we've got two sets of coordinates, so X and H, Y and J. And we simply need to ask the computer to keep asking itself a question, which is the coordinates of the helicopter the same as the coordinates of the helipad? If so, the helicopter's landed, game over. And we can easily do this with a very simple question. So we'll say at line 80, and all we need to say is if X equals H and Y equals J, then, and this is where we can then put what we want it to do. So let's say we want to go to, and let's say line 110, and then 110, clear the screen, and then 120, print, open quote marks, well done. Should be a space between well and done. There we go. Okay, let's CLS. Just list how that looks. Not looking too bad at all. Let's run, see if that works. So if I now bring the helicopter down to the helipad. There we go, we landed. Well done. So that is a very, very simple game that you can do. We've just done it in, what, 20 minutes or so? CLS, I'll just list it one more time so you have the source code. Now, the CLS commands is the reason why we're getting that strange flickering. And there are ways to combat that. We won't cover that in this video, but just want to keep things simple. Let's just find out before we finish how much memory that all took. So again, we just go question mark 3, open close brackets. So yeah, we've still got a good 770 bytes of memory available.
So there we have it. There is a quick introduction to BASIC and programming on the Raspberry Pi. Really hope you've enjoyed this video. Thank you for watching. If you need any assistance or want to drop any comments, please feel free to do so in the comments box below this video. And don't forget to like and subscribe to us here on Wi-Fi Sheep. We'll see you real soon. Bye for now.